Smooth surface, yeah. That was an amazing, amazing answer. So she said because it's a smooth surface. I'm just gonna write smooth surface.
Do you want us to write
No, don't write this down. We'll write down the next one.
No.
Smooth surface.
Everybody
You said photons go into our eyes. Okay. Photons, and then like this, go to our eyes. What else do we have? That you pretty much said a lot of good stuff there. Does anybody else have any other ideas? Get this on me.
It has to do with light.
Has to do with light, absolutely. Sorry, Cody, there you go. Any other thoughts? Why do we see reverse mirrors? No? Okay, well, you don't have any ideas. Well, I've got a couple.
Mirrors are complicated.
What's that?
The mirrors are complicated.
Mirrors are complicated? Yes, but they're also simple in a way too.
It's just light and
There's
stuff.
two things. What's that?
It's just light and stuff.
It's just light stuff, yeah, exactly.
Light bouncing.
But there's two things we need to understand why we see reversing mirrors, okay? The first one is a really big term that I would write at the top of your page. It's called rectilinear propagation.
Oh,
What? You write that down on the board.
Rectilinear propagation, right here. Oh, almost. There we go.
Propagation, what does that mean?
So rectilinear propagation is a huge word that all it means is that light moves in straight lines. That's all it means. Light moves in straight lines. So how we know rectilinear propagation is a thing, or how we know that light moves in straight lines, is we can test it with something called a pinhole camera. Has anybody heard of that?
No.
No? Okay. Well, you're going to see one on the next slide here. Boom. So a pinhole camera looks just like this, just like the box here. So basically what happens is there's a tiny little pinhole, that's called a pinhole camera, and the light enters here, and because of the way it enters, we can't have light from here, from the bottom, come up and then go down here, right? It travels straight and it goes right to the top. Light from the top travels straight and it goes right down to the bottom. So we actually get a flipped image.
And then we flip
Okay.
it with her.
So this is what a pinhole camera is, and it proves it because the image is flipped. Does that kind of make sense for you? Yeah, Haley? The rectilinear propagation. Here, I'll go back and show you where it is. What it looks like. It's right here, in the red.
Okay.
Rectilinear propagation. Light travels in straight lines.
Should we write down that like whole slide of information or?
I would not. No, I would just write rectilinear propagation. Light travels in straight lines. That's all I would write. Okay. So you could actually test this. What I wanted to do today, but I couldn't get enough material for us, is if you light up a candle and you've got two cards. You've got a black one that where you can see the reflection, and you've got a white one, and you just poke a hole in the white one, you'd actually be able to see that flame. It would flip over on the other side. So we could actually test this out. So if you have a couple things at home and you want to test it, just poke a little hole into a flame, or if you have a fire burning or something like that in a dark room, you can actually see this occur, okay? And then they're just showing what that would look like here. So here's a candle, the light from the top of the candle comes down, and we would get a flipped image of the flame right here. Okay. Now, the next thing we need to understand is how light reflects. So I'm going to mute this for a second. I'm going to turn this back on. Oh, there we go. So if we're playing hockey, let's say we're playing hockey, we've got the boards right here, and who's playing? I'm going to say we got Big Al right here.
Back in his novice.
And Al, who are you passing to?
Toronto.
You're passing Cardinal, okay. And Cardinal's right here. We're gonna say this is Cardinal. There we go.
Great team.
And Cardinal's always smiling, so we'll do that for him. Okay. So if you were trying to pass Cardinal the puck, I'll put a C for him there. That's Cardinal. How would you wouldn't hit the puck against the boards right here. You got a defender right in the way, okay? You wouldn't pass the puck right here, would you?
No.
Where would you pass the puck? Where would you hit the board?
Saucer between his legs.
Where he is, like,
Right up here?
yeah.
Just
Okay, something probably like if you want the puck to go right to his, let's say he's got a stick right here. You want to land the puck right there. You probably go something like that, eh?
Yeah.
Does that make sense? Right. So particles always move this way.
That's okay.
Whatever angle it hits the boards at, it's gonna come out at that exact same angle.
How do we
Okay.
beg to
You can do the same thing
Yeah.
with like billiards. If you play pool, it's the same thing. If you want to make one look like a bank shot, you just have to realize that it's going to come off at the exact same angle that you hit it at, unless you spin it or something, right? So particles always move this way, no matter what. Even atoms, all those things, waves move the exact same way. So how we explain this in science is we say the angle of incidence equals the angle of reflection. Okay, and I will write that right here. Sorry, Alan Cardinal, I have to erase it. So the law of reflection means that the angle of incidence so that's the passing of the puck, right? And then once it hits the boards, we have the angle of reflection. I can't talk today. Angle of reflection. Okay. So I'll get out of your way. Over there. So using these two concepts, that light moves in straight lines, and that our angle of incidence always equals our angle of reflection, we can kind of piece together why we see reverse in mirrors and how light interacts with mirrors, okay? So what I like to do when we're talking about mirrors is use little arrows. So the one I'll use it without a top, I'll go like this. Just like a one-sided, oh, let's say, it's called a flag. And we've got this. You may as well draw this along with me. I think this might be a good one for you to have. And I'm gonna find my meter stick just so I have straight lines. And I'm also gonna draw a little eyeball down here. So this is, who is this now? I'm gonna say this is Kyle right here, and Kyle's watching this flag in the mirror. This is, Kyle, are your eyes green? No. Blue? Okay, no, I'll get your eyes right. Sorry, Kyle.
He's taking a lot of time into the aspect of the person.
There we go.
Good teacher.
There's Kyle's eye. Alright, so light from this flag is reflected in all directions, okay? Let's just look at the top of the flag. It's got light coming this way, it's got light coming this way, that way, but none of that light matters. The only light that matters is the stuff that makes it directly to Kyle's eye, okay? So using the angle of incidence equals the angle of reflection, and that light travels in straight lines, we know that light's not going to go like this to make it to his eye. That's not how light works. It travels in straight lines. So it has to hit off this exact mirror and come off at the same angle. So it's probably something like, let's say we're going from the top, probably something like that. And it's going to come and hit his eye at the same angle. Okay? And all parts of this flag are going to do that. So it's even happening right at the bottom of the flag here. Oh, that wasn't a very good one. I'm going to try that one again. So, does everybody, I get this down, Cardinal, you might need it. You might need it in a bit. I'm gonna do one more. I'm just gonna use the very, very tip of the flag here. So I tried to use the top of the flag. I'm gonna use the tip of it. Make one more.
From there.
Okay. Now that we have this part down and we see how the light hits the mirror and hits Kyle's eye, now we can form what that image is gonna look like. Okay? So in plane mirrors, how we do that is we know that the image is always gonna be on the opposite side of the mirror. Like when I've got a mirror here, if I hold it up, it appears that like what you see in the mirror, if you're looking at yourself, the image is actually behind the mirror. Okay? So it kind of looks like you're behind, even though you're out there. So I'm just going to show you what that looks like on the diagram here. The flag will be something like that. Now, what I could do is I can actually trace these. I can use the exact same lines to find out where it's going to be. So if I set my ruler up like this, I'll just make a dotted line. So this part of the flag, the very bottom, it's going to hit my eye, and it's going to appear to be right there. That's where that photon of light is going to appear in the mirror. I can do the exact same with these two as well. Okay, so the top of the flag is going to be up here, and then the tip. So it's going to be right there. So, in a mirror, the object is going to, in this kind of mirror anyways, in a perfectly straight mirror that's smooth, like Jacqueline was saying, the image is going to look the exact same. Does this look like that?
Yeah.
Kind of.
Not
It's
really.
not very good, it's not a perfect drawing, because my angles weren't perfect, okay? But in real life, this image is going to be the exact same size and the exact same distance away as this one is, okay? So it would be something like that, and these lines would meet up with that, okay? Now, we explain this mathematically. We say that the distance from the object to the mirror, we call that DO. Okay, that's distance of the object. I'll write that down. We also have DI, distance of the image. And that's distance from the mirror. I'll add from mirror in here, just to get confusion out of there. And then DI, distance of the image from the mirror.
Mr. Morrow,
Yes,
I really think it was.
absolutely, you can say. Now there's two more ways to describe this image. We can talk about the height of the object and the height of the image. And so it'll be the exact same thing. We'll call that HO. And we'll call that HI. Okay? Height of image. And the height of the object. Now, we're going to come back to these four things in our second portion. We're going to come back to that in magnification, okay? We're going to come back to that right here, right after your break.
Oh, we get a second break now.
Oh, you get a second break now. Yeah, that's what you told me. It'll be a quick one, but I'll give you that. Now, using what we learned about rectilinear propagation and angle of incidence equals angle of reflection. I want you to take 3 to 4 minutes to tell me this. Okay? Could I get, I need one volunteer, please.
I'll do
Okay,
it again.
Cody. How big do you think this mirror is?
Like in like square feet.
No, just like from top to bottom, like 3 feet tall, 4 feet tall,
How tall are you?
3 feet, 6 feet, let's say.
Yeah.
It's not focusing.
3 feet? Okay, that's okay. I'll go over here for you. There we go. Hands to me. Can you see all of your body in there, Cody?
No.
No, you can't? Come over here for me. Do I need to tilt the mirror at all?
Oh, like down.
You're tilting it
Down?
upwards.
Well, like in that way. Like up. I think I'm just too close. But look at that handsome pillow.
Right, Anna, can you see your whole self?
You realize this is being recorded, right?
Okay.
I feel like you're just being picky. There's no way you can't see yourself.
Well, I can't see my
He
boobs.
can see himself, but it's not his
He's
whole
not
body.
sure.
Can't see my boobs.
Okay, you can't see
Your
it.
boobs are under this thing.
Okay. You're gonna
You see
need back
yourself?
up. You're gonna need to back up a little more.
Stand up on the
There
thing.
is a way that Cody can see his whole body in this 3-foot mirror. Okay?
It's just you have to be fine.
Yeah, okay. So tell me what Cody needs to do to see his entire body within this mirror. And try to show me a diagram of what that might look like. Okay? That's my goal for you for the next 3 to 4 minutes. And then we'll come back and we'll do it together.
We're going to work on this together.
Yeah, absolutely can. Yeah, alone, together, whatever you like.
What do you think of my how you could do it? Because you're really close to this image. If you're really close to it, even if you're really close to it, the image. If you're really, really far away, even though they're really tiny, you can see it.
I heard somebody. Was that you, Danny?
Can you use the washer?
Yeah, go for it.
Did you get it? Where am I sticking in?
Can you look yourself in the eyes in the mirror?
Yes.
Yeah. How does it like? What, you have to look at it very straight. Can you look yourself in the eyes in the mirror that you're bigger than?
Yes. Yeah.
You're overthinking this.
Yes, go for it. Well, I should stop recording right now.
Can I see a little bit, you know, or you?
Yeah, absolutely can.
I don't know, pull it off here.
Have you almost looked at all of our final projects for the last unit yet?
What's that, sorry?
Have you almost finished your
No.
final projects for the
No,
last
we
unit?
haven't.
Is it way too long?
Yeah, we're busy.
You already come over?
No problem. Brad? Oh, no, we hit.
Did you always leave it like wherever you left it? This is it.
Do you like my stick on just by your hair?
Yep. did not give you two of these yet, did I?
No, you always miss us.
I know I do.
We're right in front of you.
Good morning. Yeah. All right, let's turn back to the class, back up here. So does anybody have any thoughts on how that might be able to occur? How you might be able to see your full body in a mirror that's not quite as tall as you? Let's go. I saw Haley's hand first. If you sit down, that's a really good answer. Didn't think of that. Yeah. Yeah, absolutely. So you said just if you go far enough back. Why would going further back help you to be able to see more?
Because it's distance
Any ideas?
from object.
With what we just talked about.
Distance from object and that sort of stuff.
Hey, I like that. Yeah, with the distance of the object, the further the distance, yeah. What number is it on this sheet? Extension number 1 is that exact same problem. So we'll try to solve it, and I've got a graph of what it will look like. And we'll show that in a little bit. But I want to show you one more thing before you get going on this one. So question 2, you'll see it's got the football in there. It's basically the exact same thing we did up here. I just want to see if you can do it. The first question is a little bit different though. It doesn't have the eye with it. So how might that look? Any ideas?
Straight.
What's that, sorry, Jacqueline? Yeah, it's got no eye. So we use the eye as a reference point to see where that light will concentrate. But if there's no light, what I like to do is I like to use arrows. So I'll show you an example up here. So if I've got this arrow,
There.
and this here, and I'm gonna get my ruler back. What's gonna happen if the angle of incidence equals the angle of reflection, and this comes straight at the mirror, where's it gonna reflect to?
Straight back.
Straight back, exactly. So we've got a ray going this way. It's also gonna shoot right back in the same direction. That means when I'm looking at the image in the mirror, it's gonna keep following this line, and my image is gonna appear over here. Okay? And I can do the exact same thing up top. And I'll go like that. What would happen with a, because not all photons go that way, right? There's some light that goes this way, that way, this way. What if I had some light go right up here? Where would I see that in the mirror? Any thoughts? Any idea? It would be the exact same thing. We'd have to find this angle here, and we'd reflect it. It would be something like this, and then we just continue on that line. Okay? Does that kind of make sense? Okay, I'll get you started on this, the first one that I just handed out, and then we'll go over it all together, especially the back page. The back page I haven't gone over. So just try to figure it out yourselves, but then I've got some graphs on the PowerPoint that I'll show you that I think will make a lot of sense for you.
So you're just mirroring
It's a little
the
bit
image.
small.
Absolutely, yeah.
So we kind of did this already. We've done this in math before, how when we have to do like the graph and do it opposite.
Right, yeah, same thing.
We just go do the arrows.
Yeah.
Okay.
It's like maybe what
So like when we do the arrows, we just do this. I don't have a.
Yeah, ruler will definitely help.
Side of calculator if it's confused, or side of their cell phone? Straight edge of any kind?
It's a rough